All right, everybody. Today, the goal is just to give a broad overview of the main concepts and calculations in the course thus far. Now, obviously, it's been 8 weeks, and we can't go into a lot of detail, but I hope to give you a chance to ask questions about the main things. That's really what we're going to do. There isn't a notebook today, but I do have last time's notebook open if people have questions. The midterm is this evening. The main thing for you now is to relax, right? If you get yourself over anxious or feel that you have to spend every minute between now and the exam studying, that's not necessary. You have worked hard and you're going to be fine. Students ask, well, what should I do? Because I feel like I should do something. My suggestion is you focus on what you know best, actually, because that's where you're going to do best. If you have a little time, you may look at some other things, but really don't feel like you have to be studying. During the exam, my recommendation is that you don't rush and just read the question carefully and answer the question as stated. And you really will be fine. I think, Professor David, I'm going to ask you to give your suggestions too, please.
Relax. You'll be okay. You'll get through it. If you get stuck on a question, don't spend too long in any one question. If you get stuck on a part, check whether you can do the next part. Maybe come back to that one later. You'll get through it.
So there will be no homework released today, but the routine starts back up on Monday. So let me actually just give you a sense of what there is on the slides, and maybe you can advise me on, can you see the list of titles on the slides? You can't anymore. How about now? Yeah. So we have an overview of array and table operations, notes about simulation, how to generate random samples. Do you see these parentheses in here? Those are section numbers in the textbook. And I've given you a few key section numbers. If you want to do anything, it's maybe worth looking at those. So we have table operations, functions, histograms, calculating chances, and then like quite a lot of slides on testing hypotheses. So what I'm going to do is just get started and keep the chat open. Is there a preference among the people who are here about what to focus on? So there's already a vote for testing hypotheses and probability. Simulation hypotheses, probability and hypotheses. Simulation hypotheses, probability. It seems okay. You know what? I think we have a lot of interest in what somebody has described as the newer stuff. Okay. I don't actually think we need a real poll here. This is pretty clear. Okay, so let me go through. The first part of the class was about getting you familiar with computations at all. And the main structure with which we do computations are arrays and tables. There are two of them. And so array operations are element-wise. Two particular operations that we use quite a lot are appending. Like you start with an array and you tack on another value to it. That is done every single time you do a simulation. So np.append is good to know. Very often we count how many elements in an array satisfy a certain condition. Often, is it bigger than or equal to something or less than or equal to something? And that is done by either sum or np.count non-zero equivalently. So these three, sum, np.count non-zero, and np.append, are worth keeping in mind. Professor David, any other notes on append? On arrays before I get to tables?
No.
All right. Tables, there are the manipulations with a single table. That is, you take, select or drop columns, you select rows in different ways. You can add a column or columns, that should say, to the table with columns. You can sort, and you can apply a function to every value in a column. And that method is not surprisingly called apply. So select and drop, where and take, sort, all of these evaluate to tables. What we should have put in here is you can extract the elements in a column as an array. Dot column is used a lot. And that's when you want to actually work with the numbers or the strings that are in a column. And then there are the operations that one operation joins two tables, and the two tables have to have something in common, which is each table has to have a column that contains labels that are identified with each other, right? So you have to have information in one column that is also in another, so that join knows how to match. Professor David, do you want to say something that is a little more coherent than that?
I saw people asking about how to choose between pivot and group. So maybe I'll comment on that.
Great, thank you. So you want to take the next two bullets?
Sure.
Thank you.
Suppose you want to break down the data into some groups and summarize each group. Then you can use either group or pivot. If you want to separate the data into groups based on the value of one variable, like split up by gender, or split it up by what year you are, freshman, sophomore, junior, senior, that would be splitting things up by one variable, then use group. If you want to split it up by two, then you've got a choice. You can either use pivot or group, depending on how you want the results presented to you. If you use group, then there will be one row per combination of the two variables. If you use pivot, then there will be one cell per combination.
I'm answering the question, is the third column, is the third argument for join optional? So the third argument for join is the label of the column in the second table that join is supposed to look for the identifiers. If that column label happens to be exactly the same as the label in the first table, then you don't have to use it. Do you recommend reading all the questions first? That's really up to you. I recommend reading a few. If, I would suggest if you read a question and you feel like, yes, I can approach this, then go for it, just do it. But if you read a question and you feel that, it's not making you feel great, read the next one. Where to use pivot versus group? Okay, I tell you what, I am going to go, so really, if you have two categories, two variables that you are grouping by, then you can use either. Okay, so I had a ton of requests for probability and testing hypotheses. Let me go through that. And then in time remaining or on Ed, we will continue with these because with the pivot and group. So this was a big ask. So simulation, drawing random samples is a fundamental part of this class. And there are 3 methods. And the methods, which one you use depend on what you are drawing from. So if you are drawing from an array of values, that is, if you're drawing from a bunch of cards and the cards are all in an array, then np.random choice is a great thing to do. It by default, the methods all sample with replacement. The slides should already be posted. If not, they definitely will. If you start with a table, then table.sample helps you sample rows. By default, it samples with replacement. You can, if you want without replacement sampling, that is simple random samples, then you can add with replacement equals false. By default, if you don't give it a sample size, then how many does it sample? All. It samples everything. The place where we have used it is to permute all of the rows of the table. In particular, then that was used for permuting all the labels that the individuals had. If you have a categorical distribution, right? So red, blue, green, purple, and you have the proportions in those, and you just want to sample from that, and all you are interested in are the proportions in the sample in the different categories, then sample proportions is a great way to go. The difference between sample proportions and the other two is sample proportions doesn't show you the whole sample. It aggregates the data and shows you the percents. It doesn't show you one by one which one was in which group. Why is np.random.choice the odd one out for position of sample size? np.random.choice is a Python method from the NumPy random module. The others are table methods. And so in our minds, it's, you take these data and you sample these many times in this way. So that's really it. That's the reason. Okay. So these are the 3 methods, and you choose based on what you are starting with. Is sample size just a number? np.random.choice does operate without replacement. I believe the option is replace equals false. You don't have to worry about that. We have been using it with replacement. That's fine. In A/B testing, do we sample with replacement or without replacement? We are shuffling all of the labels, right? So if you have 52 cards and you shuffle all of them, is that a with replacement method of sampling or without? Without, right? Because you can't have the same card appear in 2 places. So therefore without. Is there a reason we sometimes multiply sample proportions by 100 if you want percents, right? It gives you np.random.choice picks with replacement by default. Okay, moving on. So if you want to simulate a statistic, by the way, if there's one section you want to read about simulation 10.3.3, it just lays out the process, and you check every one of our simulations is done exactly like that. You first define a function that returns one simulated value. You make an empty collection array, you run a for loop, you call the function every single time. Why do you do that? Why do you need to call the function every single time? To generate a new sample so that you get a new value of the test statistic. The point is that these functions call one of the random sampling methods. So every time you run the function, you get a different answer. Okay, so you call the function and then you append the newly simulated value to the old array, and don't forget to name the array. Okay, and so the next two slides give you examples of these. So here is a function that I think the bet was you're going to roll a die once. If the number is 1 or 2, then you lose. If the number is 3 or 4, then there's no change to anybody's fortunes. And if the number is 5 or 6, then you win $1. Okay, so somebody explain to me, why did we use np.random.choice here? Because it's a natural thing to write the numbers 1 through 6 in an array, right? And you do need to know exactly which one you are drawing. It's not enough to have the proportions. So yes, so this function returns the amount of money that you win on one bet, and then to simulate the net, the amount of money that you win on each of 5 bets, you make your empty collection array, you make a for loop that runs 5 times, and then you call the function once, and then you append that value to your collection array, but remember to rename remember to assign it to the collection array. Otherwise, the appending will happen, but then it will just disappear into the ether. np.random.choice assumes equal probability for each element of the array. That's quite right. It picks uniformly from the array. That's a good point. Okay, histograms, reading histograms is a good technique. The key to histograms is when you're looking at histogram, you're looking at areas. You're looking at areas, you're looking at areas, you're looking at areas. And so quickly, stare at that. Which bin has more people? $10, $15, or $15 to $25? Which bin has more people? What are you looking at to make that decision? Okay, I've already had 2 numbers. Okay, so you're looking at area. Exactly. Area represents proportion, hence also percent, and counts. Area. So which of those 2 bars has more area? 15 to 25. You do not need to do a calculation. You can see that. All right. Now, if you want, in this case, you can calculate the area. This thing is a rectangle. Its height is 4% per $1 million. Its width is $10 million, and therefore 40. But if you did not have the numbers on the vertical axis, you could still have answered part A. Yes, no, or maybe. You could, by just visually comparing the areas. That is very, very important to know when you do a calculation. What is the minimum information you need to be able to answer? Okay. If you draw 1 bar over 10 to 25, how tall will it be? So this bar is going to go from 10 all the way to 25. I have a question for you. Okay, the bar is from, at the first bar, 10 to 15 is at 5. The next bar over 15 to 25 is at 4. Is your answer going to be equal to 4, equal to 5, or how else could it be related to 4 and 5? Somewhere in between. Exactly. Somewhere in between. The crowdedness in your first bar is 5% per $1 million. The crowdedness in your second bar is 4%. If you combine the two, you're going to get somewhere in the middle. So if you draw a bar from 10 to 25, how do you figure out its height? How do you figure out the height of any bar in a histogram? What do you need? The bar is a rectangle. So what do you have to do? You need the area and you need the width, right? So if you go 10 to 25, what's the width? The width is 15. Terrific. How are you going to find the area of that imaginary bar? You are going to add the area of the 2 bars. Why is that? Because the area is the percent in the 10 to 25 bin, which is the percent in 10 to 15 plus the percent in 15 to 25. So you will add the area. This first area of the 10 to 15 bar is 5 times 5, that is 25. The second one we said was 40 already. So the total area is 60. You're going to take 60 and divide by 15 and you'll get 4 1/3. And the units are 4 1/3% per $1 million, the same units as you have on the vertical axis that represents density. So the question I think that is being asked, 65 divided by 15. Yes. Can you make conclusions within bars? Actually, if you just have the histogram, you cannot make exact calculations, because the histogram is just telling you, for example, in this bar, 15 to 25, that there's 40% of the entries in this interval, but it's not telling you whether they're all bunched up in one side of the interval or not. So if you just have the histogram, you cannot make conclusions within bars. You can make approximations perhaps, right? But you can't make conclusions. All right. Calculating chances. All right. So, there are a bunch of rules. There's a formal looking mathematical formulas, but I suggest that we just step back from all of those and give ourselves a way of calculating chances. Now, I'd like to be clear that we are calculating. This is in the situation where you're asked to calculate an exact chance, and there is some event described. So this slide I took from this is slide 11, lecture 14. I would say the most useful slide on calculating probabilities. If you got to read one slide, read this one. Okay. In all of these, just go through this routine. Ask yourself what the first trial has to be. If there is a clear answer, ask yourself what the second trial has to be. If there is a clear answer to that, your answer to your question is almost certainly going to be a fraction of a fraction of a fraction of a fraction, and you're done. If there isn't a clear answer, well, it could be this or it could be that, but if it were this, then the other one had to be that. Then start listing the ways. All right, list the ways, list all the ways, find all of their chances and add up. If the list gets long, then think about the complement. And if you are lucky, the list for the complement will be shorter, and then you can do a 1-. So I would ask that you go through every one of these steps, unless you are extremely confident about how to do this, because otherwise it feels like guesswork. But it's not guesswork. So we will take 2 examples and we will see how to, okay. So I have 4 green tickets and 6 red tickets, and I am going, that's 10 tickets in all. I'm going to draw 3 times at random with replacement. Probability, please, please, please read the question and somewhere mark in red whether it's with or without replacement. The complement is what would happen if the event didn't happen. Okay, so I'm going to ask you, what is the chance that they're all green, all red, all same color, and at least one is green? And we're going to go through the thought process. All green. Okay, so this event, what does the first one have to be? Not a fraction. What color does it have to be? G. What does the second one have to be? Also G. You're in business. 4 in 10, and then times. Now, this is where you pause. This is where you ask with replacement or without replacement. And it is with replacement. Exactly. So 4 in 10 times 4 in 10 times 4 in 10 times 4 in 10. Sorry, no, only 3 times. I got to stop. Okay, terrific. If we play the same game with all R, then you agree that it's going to be exactly the same thing, except with 6s instead of 4s? Okay, let's try all the same color. I'm going to go through my routine, right? I'm going to ask myself, what does the first one have to be? My answer is I don't know, right? Well, okay, can I say something about what does the second one have to be? Well, it depends on whether the first one was red or green. If the first one was green, then the second one has to be green. So I'm going through this, and I'm noticing that there are multiple ways this can happen. So I write out the 2 ways it can happen, which is all green and or all red. I find the 2 and I add up. So notice that I never use the term addition rule. It's fine, but I think the logical process is a better idea. Okay, so at least 1 green. So at least 1 green. Well, the first one could be green, the rest could be red, or the first one could be red, and then some of the others could be green, and there's a lot of different ways it can happen. Right? So I can start listing the ways. My list is long. So therefore, I try the complement. What is the complement of at least 1 green? No green. And I know how to find no green because no green means all red. Okay, so I will not get into and implies multiplication and or implies addition. It really depends on, let's think in terms of, instead of thinking in terms of keywords, let's think in terms of logic. If you want a lot of events all to appear, then your answer is going to be a fraction of a fraction of a fraction of a fraction. That's multiplying fractions. If you are satisfied with either one of a bunch of ways it can happen, you can add the chances provided you have split the event cleanly. So you have probability of all green that way, all red that way, all the same color by listing the ways, at least 1 by doing a complement and noticing that we have found this probability before. When answering probability questions, you can use any format that we can read and understand. That's fine. Okay, what we're going to do in the next slide is we're going to see exactly this, but without replacement. And I want you to notice very carefully where the differences are. Okay, so same question. Logic is exactly the same. The only difference is in what you are multiplying in these second and third factors. So I will, here's slide 19. Let's look one more time at slide 18, which someday will pop up, which is, these are too fancy. Okay. The only difference is in the fractions that you use in the second and third factor. Okay, I will pause for a second and take questions. This routine works every single time. All right, so if you have doubts about how to do these things, go through the routine and it'll work. Okay, so this is the main business of how is P at least the same for with, it is not the same. The logic is the same. It is 1 minus the chance of all red for both of them. But the chance of all red is a little bit different for with replacement versus without replacement. Does that answer that question? In both cases, it is 1 minus the chance of all red. But the chance of all red, the second and third factors, are different. Will we be given skeleton code? There could be skeleton code or not. Okay, so testing hypotheses, people get very drawn into the simulation and what has to be calculated, but much of the test, much of what you're going to do is decided before you touch a computer, right? And so the key is read the question, figure out the viewpoints that the question wants you to test, not necessarily what you think ought to be tested. By the way, the key section for this is 11.3. Okay, the null hypothesis, as you know, is the completely specified chance model. So when you state a null hypothesis yourself, make sure that you are saying where the chances are. All right, so if you say each one has proportion 1/6, make sure that it's better to say each one has chance 1/6, or you are drawing randomly from proportions, all of which are 1/6. But please make sure that you are saying something about the randomness. Okay, the alternative hypothesis comes from the question again, all right? So look at the question and see what is the opposing viewpoint. If in the question somebody is saying, nah, the model in the null is not great, then that's the alternative. If in the question somebody is saying, nah, there's the model in the null is not great, there are too many blue people in my sample, then that is the alternative. There are too many blue people. That's a very specific thing. Okay, and then you have an alternative that has a direction, but it comes always from reading carefully the question. Okay, and then you need to decide on a test statistic that chooses between yeah, so the null and alternative don't have to be complete complements taken from the entire set of possibilities. Is it possible to have different opinions to pick, different options to pick from for our alternative? The alternative is determined by the questions that are being asked in the analysis that you're doing. You may have different options of test statistics. Let's come to that. You need to, how do we know when to include directionality in our hypotheses? First, the directionality is only going to be in the alternative, and you will know based on reading the question. The question has some viewpoint, and if that viewpoint has a direction, then that's when direction comes in. When writing null ourselves, should we always include any differences due to chance? You don't have to. You just have to specify the chance process that is drawing the sample. The test statistic is a numerical value that is computed based on your random sample. That is correct. Okay, so now there's a question of how do you decide on your test statistic? By the way, how do we decide on a test statistic like TVD versus using A/B testing? A/B testing is not a test statistic. A/B testing is a method of testing. All right, so it's never a TVD or A/B testing. It's a TVD or a difference, perhaps. Okay, so okay, to choose your test statistic, look at the alternative. If your alternative is just not the null, all right, then you need something that measures distance from the null hypothesis. So somewhere there you are going to have absolute values. All right, and distance, the way you have looked at distances are very commonly, you have some categorical distribution, maybe two categories or more than one category, more than two categories. Then you can use total variation. If you have two numerical samples, and then you are looking at whether the underlying distributions were the same or different, you might look at the distance between the two sample averages. Somebody asked earlier if when a direction is specified in the alternative, it is a sign not to use the TVD. Correct, absolutely correct. When you have a direction in your alternative, you cannot use any kind of distance because the distance hides the direction. So there are two testing methods, hypothesis test and A/B test. Actually, no, there is one testing method, hypothesis test. A/B test is a particular case of a hypothesis test. How do we determine our testing method? Once again, A/B testing uses a test statistic. So let's be clear. It is not that you use a test statistic or A/B testing. In the A/B testing examples that we did, our test statistics were the difference between the two averages or the difference between the two proportions. Yeah, we'll do examples in just a moment. Let's do the generalities first. Okay, so if you do not have, if your alternative specifies a direction, then you are going to use a number like a count or an average or a difference from what you expect. And you are now going to think, you haven't done any calculation. You are now going to decide, for my p-value, am I going to look right or am I going to look left? And for that, once again, you go to the alternative. And you see what kind of values of your statistic favor the alternative. If low values, then you are going to look left from your observed statistic. If high values favor the alternative, you are going to look right. You have made all of these decisions before you have calculated anything. It should not get to the end of the calculation where you start thinking about, am I going to look right or am I going to look left? That is all part and parcel of choosing the statistic. Okay, so then we get to what exactly is a p-value? It is the area of a tail, which is the tail that's always, always, always starts at your observed statistic and then moves in the direction that favors the alternative. All right, in this case, the statistic that we used was the number of heads. The alternative was biased towards tails, and therefore the low values of the number of heads favor the alternative, and therefore we are looking left. Okay, so is this something we have to memorize? That if the p-value is low, then we favor the alternative, and if the p-value is high, then it's consistent with the null? No. If the p-value is low, then the tail beyond your observed value is small. That means your observed value is way away from the bulk of the null predictions, right? It's at an edge of your distribution. Maybe it's way even beyond an edge. Okay, so that value is not looking consistent with the null distribution. All right, so now, okay, so here, how do you know whether to use less than or equal to or greater than or equal to when calculating the p-value? It is part and parcel of your decision whether you're going to look right or whether you're going to look left. If you are looking right, are you not looking at how many values were equal to your value or greater? The person who asked that question, you agree? If you're looking right, you're looking at all the values that are greater or equal to, there you go. That's your decision, right? If you're looking left, then you are looking, then you're looking at less than or equal to. Yes. Yes, okay. If the p-value is exactly the value of the cutoff, do we accept or reject the null? You know what? I wouldn't worry about that. The chance of that happening exactly 5% with so many replications is not worth thinking about. And the other thing is, this is where you keep in mind that the cutoff is purely something somebody chose, and you are perfectly welcome to say you cannot make this decision based on this test. Okay. So the p-value is a chance. It is computed under the null hypothesis. And it is a chance that the test statistic is equal to what we got or even more like the alternative. All right. I am going to look to see what comes next. Okay, the next one is chance of error. If you use absolute difference or TVD for the test statistic, that just means the alternative favors large values. Let's take it in a different order. If the alternative says that the null isn't good, you're just looking for null or not null, that is when you choose a distance. Large values of distances mean that you are getting a difference from the null, and that is why large values favor the alternative. If you do A/B testing and the alternative is just that there is a difference in the two samples, can we use TVD as a test statistic? Okay, I think this is this, I answered this to the same person on ed, but let me take it from here. Supposing you have A/B testing, and what you are measuring are categorical distributions, right? So you have a sample of green people and a sample of blue people, and you're looking at their employment status. And you want to know if those the employment status distributions are the same. Then if your alternative is the distributions are different, then you can use TVD, right? The TVD measures distance between two categorical distributions. So you should not be thinking about that unless you have a categorical distribution. Do we only use TVD when we are concerned about the entire categorical distribution and not just the probability of one factor? That is a fine way of thinking about it, right? I mean, honestly, if you just think about the proportion in one category, where the others you just lump into other, then that number, that distance that you compute, that proportion in the sample minus the proportion that the null predicts, that distance that you compute is actually equal to the TVD. If you look at section 11.3, we actually have an argument about that. Okay, RCT, I'll come to that in just, what is an example of a non-categorical distribution? The birth weights, numbers. We do not use any distance when there is a direction in the alternative, quite right. Okay, so now what does the cutoff mean? It is, so somebody decides on a threshold. Sometimes we allow you to decide, sometimes we tell you what the threshold has to be. The point is that this threshold measures how wrong you can be, how often you will be wrong if the null hypothesis is true. Section 11.4, and the point is that the researcher gets to choose the cutoff so they can control the error probability. If you say something is the TVD, then you better be dividing by 2. Okay, the cutoff does not depend on the data. It is a decision you make well before you have even started your gathering your data, right? It's made in the protocol of the study that we are going to decide that probabilities of less than 1% are small. Okay, so what affects? Okay, if you divide by the TVD, if in the TVD calculation you decide to divide by 3 or 17 or 184, you cannot call it the TVD. You can call it some kind of distance, but that is not the TVD. It is TVD times a factor. The TVD has a very specific definition with the 2 at the bottom because A, for 2 categories, it is the same as the distance between the proportions, and B, it has an interpretation as a probability that you can learn about in some other class. The paper did not divide by 3 for the TVD. It said that dividing by 3 gives you a statistic that you can use. It's a different statistic. It is not the TVD. It happens to be TVD times a constant. Okay, factors affecting the p-value. Okay, true or false? The p-value depends on the null hypothesis. One person says true. Okay, so we're not absolutely sure about this. Well, so what you look at the tail area in some histogram, right? That histogram is computed under which hypothesis? The null. So does the tail area depend on the null hypothesis? Yes. Okay, great, terrific. Does it depend on the alternative hypothesis? Yes, no, or maybe. Okay, so how did you decide which tail to look at? Based on the alternative. Exactly. Therefore, the p-value depends on the alternative. Next. Does it depend on the choice of test statistic? Well, all of this depends on the choice of test statistic. Does it depend on the data in the sample? Yes, because it depends on your observed test statistic. Does it depend on the cutoff? It does not depend on the cutoff. The p-value is what you see in the tail. Once you have found it, later you compare with the cutoff to decide whether it is small, but you do not use the cutoff to determine the p-value. Right. All except the cutoff. All right. So based on tail area, all right, start at the observed value of the test statistic, look in the direction that favors the alternative. Okay. Whether or not Mendel's model is good. Whether or not. So Mendel's model is good, null hypothesis with all the proportions, etc. Mendel's model is not good, alternative hypothesis. What am I going to use as a statistic? Good versus not good. I'm going to use a distance. All right. Which values of the distance are going to favor the alternative? Large. Which direction are we going to look at? Right. That way. Next example. Coin fair versus coin biased towards tails. Why to the right? Because large values of the distance favor the alternative that the model, the Mendel's model isn't good. You're looking at a distance from what the model predicts. Okay, the coin is biased towards tails. I have decided to use the number of heads as my statistic. Why did I not decide to use a distance? Because my alternative is clearly directional. Okay, if this is the statistic, then what values of the statistic favor the alternative? Big ones or small ones? Small ones. Which direction are you going to look? Left. The decision is made. There we go. You can use the difference. It's not necessary. So you can use the number of heads minus, in this case, I think there were 100 heads. So you can use the number of heads minus 50. You can use the proportion of heads minus 0.5. You can use 0.5 minus the proportion of heads, whatever. You can use number of tails as a statistic, but then number of tails would be high. Yes, so you can, whatever you choose as a statistic, you have to be consistent in how you look at the, is the coin is not fair a valid alternative? It depends on the question, right? In this case, the question was to decide whether the question is, whether the coin is biased towards tails. And that's why we chose that. There is nothing wrong with using the number of tails. You just have to remember that if that's your alternative, then large values of the number of tails favor the alternative. So you should look right. You start at the number of tails that you got in your sample, which in this case would be 60, I think. Oh, no, well, I forget. No, not 60. You look at the number of tails and go right. If the coin in this example is biased towards head, wouldn't both hypotheses be wrong? Yes. And if that is possible. Yes, so if the coin is biased towards heads and you happen to be so clueless that you are testing fair versus biased towards tails, then you're going to be wrong either way. That you are absolutely right. Okay, so you know your null and alternative have to come from some understanding of what is going on. So you can transform the test statistic exactly. You can shift it, you can add a constant, subtract a constant, multiply by a constant, as long as you stay consistent with the direction. Based on this example, does it reject the null? It depends on what this area comes out to be. And I actually think it was greater than 5%. I'm not exactly sure. Okay, so we had a lot of talk about this. You have 2 random samples, which come from 2 populations. And the question, you can see that the samples are different. The question is what's going on in the populations. That is when you use A/B testing, and your null hypothesis is about always the populations, right? It's never about the sample. You can see the sample. You can see that in the sample, the distributions are different. What you're talking about is the populations. In the populations, are the distributions the same or not? And then the simulation, how to calculate the test statistic, that is done by shuffling. So I'm actually going to stop because this is my last slide. If your 2 samples were created by randomly assigning patients to treatment and control, then you can conclude causality. So I am actually going to stop now. I'm going to turn off the recording. And I will just stay.